Now let's we see the next part, that is the example for second theory, that is which theory? Absorption theory. And in that we are having the example, one of the example, that is nothing but hydrogenation of ethene in the presence of nickel. Hydrogenation of ethene in presence of nickel. So how the exact actually the hydrogenation will going to take place? Just to see, ethene molecule, this is our ethene molecule, and this is our hydrogen molecule, and in presence of nickel as a catalyst, which is solid in the nature, nickel as a catalyst which is solid in the nature, we will get over there ethane, that is our gas. Ethane also gas, and ethene also gas. Okay, we will get ethane. So just to see, this is our ethene. So what we will get? H, here H, H, H. Okay, so this is our ethane, and this is our ethene. Now let's we see, there are this catalysis operates by the mainly following steps, which are the steps, just to see. In that first step which will be there, that is adsorption of hydrogen molecules. Adsorption of hydrogen molecules, or hydrogen molecules adsorption. So just to see what will happen in this particular step, adsorption of hydrogen molecules. The hydrogen molecules are adsorbed on the nickel surface due to the residual valence bond of the nickel atoms. So what will happen over here? Hydrogen molecules are adsorbed on the nickel surface, due to the residual valence bonds of the nickel atom, due to the residual valence bonds of the nickel atom. What will happen in the first step? The hydrogen molecules are adsorbed on the surface, that is nickel surface, due to the residual valence bonds of the nickel atom. This is the first step. What will happen? Hydrogen molecule just adsorbed on the nickel surface. Consider this is our surface of the nickel, and here just adsorbed by this particular hydrogen molecules. Hydrogen molecule just get adsorbed over there. Now let's see the second step. Second step is nothing but hydrogen bonds are broken. Okay, right here H bonds broken. In the second step, H bonds are just get broken over there. No doubt in this particular hydrogen bonds are adsorbed, isn't it here? So here what will happen now? Hydrogen bonds start to break now. The hydrogen bond is smaller. Okay, H bond is smaller. That is how much bond energy which will be there, or bond enthalpy which will be there? 0.74 angstrom unit. They are having their length or bond length. Okay, then nickel which will be there, that is nickel bond, Ni bond. Therefore, hydrogen bonds of the adsorbed hydrogen molecules is stretched and it become weak in the nature. So now what will happen? The hydrogen bond of adsorbed hydrogen, the hydrogen bond of adsorbed hydrogen molecule is stretched and become weak in nature. So if it is become weak in nature, it can be easily get broken, isn't it? Now separating the hydrogen atoms, separating the hydrogen molecule just get separated, separating the hydrogen atoms, they are held to the nickel surface by chemical bond. Hydrogen atoms held on nickel surface by what? By chemical bond. What I have told in the second step isn't just see here the hydrogen bond which will be there. They are having a smaller bond length, that is 0.74 angstrom than that of nickel. So what will happen? The hydrogen bond are at the adsorbed hydrogen molecules, it just gets stretched from one another and they are become weak in nature, so it can be easily broken. And the separating hydrogen atom, they held on what? Nickel surface. So I have already told this is our nickel surface, and on this nickel surface the separating hydrogen molecules which are there, they just get held over here. Okay, I will write here like this. They are just held on this particular separating hydrogen atom. They are first get adsorbed and in the second part just get separated. This is hydrogen, this is one of the hydrogen, and here nickel surface is there already present. Here nickel surface which is already present, isn't it? This is may consider as a step 1, this is of step 2. Now just to see the steps 3, what will happen actually? What will happen in the step 3 means, in the step 3, formation of activated complex. Okay, just to see what will happen in the third step, the chemi-adsorbed hydrogen atoms, the chemi-adsorbed, they are chemically adsorbed, no? So the chemi-sorbed hydrogen atoms then attack the ethene molecule by partial chemical bond, then attack on ethene molecule by partial chemical bond. Okay, what will happen in the third step? The chemi-adsorbed hydrogen molecule then attack on the ethene molecule by partial chemical bond and the unstable activated complex is formed. So now unstable activated complexes get formed. So see what will happen here actually in the step 3. This is our nickel surface, isn't it? This is our nickel molecule which is present on this nickel surface. So in this nickel molecule, already the activated hydrogen atom which will be there, the chemi-adsorbed hydrogen which will be there, it is just present hydrogen, and it is formation of, this is hydrogen, isn't it? And this hydrogen atoms just bond with C, Here also see, here hydrogen, and formation of activated complex. This is our step 3. I'll explain neatly over here just to see what will happen. So just to see this particular structure, what will happen here, the chemiadsorbed hydrogen atoms which is there, these are the chemiadsorbed hydrogen atoms just attached on the ethene molecule. These are the ethene molecule, and they will form the partial chemical bond. This is our partial chemical bond, okay, which is, and this is an unstable activated complex. This is unstable activated complex just get formed over here, okay. Let's see in the step 4th what will happen. Decomposition of activated complex. Step 4th and 5th at once only they will have give 4th and 5th. Okay, what will happen over here? Decomposition of activated complex and desorption of ethane molecule. Desorption of activated complex and desorption of ethane molecule. So see what will happen actually over here in the step 4. In the step 4, the unstable activated complex just get decomposed. The unstable activated complex, unstable activated complex decomposed, and they will release the ethane molecule. They release the ethane molecule. Okay, then the catalyst which will be there, it can be regenerated again for the further action, and catalyst can be regenerated. Catalyst regenerated. So what will actually form, just to see over here in the step 4 and step 5, this is our nickel surface, and on this nickel surface the formation of our complex, that is nothing but ethane molecule, or formation of our molecule, conversion of our molecule ethane going to formed, and this is catalyst can be regenerated again over here. This is our step 4 and step 5. Okay, this is all about our example of which theory? Adsorption theory. Now the next concept, we start, that is nothing but enzyme catalysis. The next part of our topic, that is nothing but enzyme catalysis. Enzymes are the complex nitrogenous organic compounds. Okay. I will give the introduction first, the introductory part of our enzyme catalysis. Okay, introduction, we start. Enzymes, point wise I will give the introduction of our enzymes. Enzymes are the complex nitrogenous organic compounds. Okay, these are the complex in nature, not simple. These are the nitrogenous organic compounds which are produced by, or which can be present in, which are produced by living plants and animals. Produced by what? Living plants and animals. So what are the enzymes? Enzymes are the complex nitrogenous organic compounds which are produced by living plants and animals. Then enzymes are protein. Enzymes are protein with high molecular mass. With high molecular mass. Enzymes are the protein with high molecular mass. The molecular mass which is there, it is more than 10,000 or more than that. Enzymes are the proteins, those they are having their high molecular mass, which catalyze the various biochemical reaction. Enzymes, what they will do, a very important role they will play. Which are that role? Enzymes catalyze the various biochemical reactions. Okay, what they will do, the very important role they will play, that is nothing but they can be catalyze the various biochemical reactions, and these are therefore often known as biocatalysts. So they can also known as, or they are often known as biocatalyst. Okay, biocatalyst. So what I have told, enzymes are the complex nitrogenous organic compounds which are produced by living plants and animals. So enzymes are the protein with high molecular mass, that is 10,000 or more than that, and enzyme are the catalysts which play or which are take part in the various biochemical reactions. So they are often known as what? Biocatalyst. And many life processes are catalyzed by enzymes, and such processes is called as enzyme catalysis. So what is enzyme catalysis? Many life processes are catalyzed by enzymes. Okay, enzymes. Such processes called as enzyme catalysis. Called as what? Enzyme catalysis. Or the catalysis brought about by the enzyme, or the catalysis brought about by enzymes, called as what? Enzyme catalysis. I hope you have understood. See, what we are dealing over here, enzyme catalysis. Enzymes are the complex nitrogenous organic compounds which are produced by what? Living things, maybe of plant or animals. So enzymes are the proteins which are having their high molecular mass. Enzymes are catalyze the various biochemical reactions, so they are often known as biocatalysts. Many life processes are catalyzed by the enzyme. Such process is called as what? Enzyme catalysis. And the catalysis which brought about by the enzymes also called as what? Enzyme catalysis itself. Let's take some examples of daily life. I'll take just an example for this. That is nothing but conversion of glucose into ethanol. Okay, example, conversion of glucose to ethanol. Just to see the reaction, the enzyme zymase, which is the particular name of the enzyme zymase, which is present in yeast, can be used for the conversion of glucose into ethyl alcohol, or we also call it as in what? Ethanol. So glucose formula, yes, C6H12O6. So our enzyme zymase. Okay, so what we will get over there? Ethanol formula 2C2H5OH plus 2CO2. This is our ethanol or ethyl alcohol. Okay, this is one of the example. Now let's see the next part. There are some characteristic of enzyme catalysis. Just to see some characteristics of enzyme catalysis. The enzymes are highly specific in their action. Okay, we will see one by one. We are having mainly 8 characteristics. That first one is there. I'll see. The enzymes are, I'll write first and then I will explain. Enzymes are highly specific in their action. That is, different reactions are catalyzed by different specific enzymes. This is similar to lock and key arrangement. Okay, enzymes are highly specific in their action. That is, different reactions are catalyzed by different specific enzyme. Different specific enzymes. This is similar to lock and key arrangement. Okay, so what I want to telling you is that enzymes are the highly specific in their action. Means a specific enzyme can be used for a specific reaction itself. No doubt a particular reaction having a particular enzyme, but no single enzyme can be used for 2 or 3 or 4 reaction. It means what? How a lock which is there, we are using a lock. Isn't it? Lock is having their specific key itself to open that lock. In the same way, enzymes are also highly specific in their action. Different reactions can be catalyzed by the different specific enzymes. Okay, this is also similar to what? Lock and key arrangement itself. So, second one is that enzymes are colloidal in the nature and very efficient catalyze. Enzymes are, second one, enzymes are colloidal in nature and very efficient catalyst. They function only in a solution media. Okay, they won't function at solid part. They function only in solution media. Okay, one molecule of an enzyme can catalyze the transformation of 1 million of molecules of reactant per minute. They functions a very low activation energy. Okay, what I want to tell you is that enzymes are colloidal in nature. They will function only in the solution media. And one molecule of enzyme can catalyze the transformation of transformation of 1 million molecules of reactant of 1 million molecules of reactant per minute. They functions with very low activation energy. They functions with very low activation energy. Okay, what I want to tell you is that enzymes are the colloidal in the nature. They are in the form of semi-solid or solution in the nature, and they are very efficient catalyst. They function only in the solution media, and one molecule of enzymes can catalyze a transformation of 1 million of molecules of reactant per minute, and the functions are very low activation energy. They never need high amount of activation energy for the transformation of reactant molecule into their specific product itself, isn't it? What the second characteristics of enzyme catalyst? First, I have already told the enzymes are highly specific in the nature, like key lock. Second one, the enzymes are colloidal in the nature, and they are a very efficient catalyst, and they function at only solution media, and the one molecule of enzyme can catalyze a transformation of 1 million of molecules of reactant per minute, and they function at very low activation energy. Never the particular reaction never need high amount of activation energy. At very low activation energy also they can be easily work, means they can be transfer the reactant molecules to their respective products itself. Now third one which will be there, they increase the rate of reaction. They will increase the rate of reaction about 10 to the power of 6 to 10 to the power of 7 times more. Okay, consider the reaction which is going in the normal path, and when you added the catalyst, the enzyme, what will happen? They will increase the rate of reaction are about 10 to the power of 6 to the 10 to the power of 7 times more. Rapid reaction will going to take place over there after adding the enzymes over there. Now the fourth one, they are very sensitive to the temperature. They are very sensitive to temperature. Optimum temperature for enzyme action is optimum temperature for enzyme action is only about 37 degrees Celsius. What this particular point used to tell you that they are very sensitive to the temperature. If you know in your home, if you are familiar with curding of milk, when milk is warm, that time if you put for the curding, they can be easily get curd over there with less timing over there. Otherwise you can take a preparation of dough to your dosa and idlis. A whole night if you keep for fermentation. Temperature maintenance also very important. In a rainy season it never get fermented properly, but in the summer season you will get a proper dough over there for the making of your dosas, isn't it? So it can be given a very good example for this enzyme catalysis, means they are very sensitive to the temperature, and optimum temperature range for the enzyme action is about 37 degrees Celsius, or in the Kelvin 310 Kelvin, that is body temperature, is very important. Okay, 37 is also body temperature, no? So 37 degrees Celsius is an optimum temperature for the enzyme action. Now fifth one, they are permanently get deactivated and destroy when heated. They permanently get deactivated or destroyed when you heated above 60 degrees Celsius. Means when you just boil, you know, in your home the milk which is there, when you when you not boiled properly within 6 to 7 hours, it may just form a curd. Why? Because of this catalysis reaction. If for the permanent destruction or deactivation of that particular enzymes, we have to heat it properly above 60 degrees Celsius, means that particular milk should be boiled over there, so that fermentation or curding will not happen over there, isn't it? This is your familiar example. So what is the fifth point? They are permanently deactivated or destroyed when you heated above 60 degrees Celsius. Okay. Now sixth one. The sixth one, what they will show, enzyme activity depends on the pH of the medium. Enzyme activity depends upon or depends on the pH of the medium. That is, most of the enzymes are found to have optimum pH value. Most of the enzymes are found to have optimum pH value that is of 7.4, that is pH of blood and other body fluids. Okay, 7.4 pH, that is pH of blood and other body fluids. Okay, so what the sixth point used to tell, the enzyme activity depends upon the pH of the medium, and most of the enzymes are found to have optimum pH value. That is, most of the enzymes having their pH is about 7.4. Okay, and that is pH of blood and other body fluids itself. This is the sixth one. Now seventh one, or seventh characteristics of enzyme catalysis. Enzymes are poisoned by heavy metals like silver. Poisoned by enzymes are poisoned by or made poisonous by heavy metal like silver, mercury, etc. Okay. Enzymes can be made poisonous by us heavy metals just like of silver and mercury, and enzymes are also destroyed by certain substances, and also enzymes are destroyed by certain substances like HCl, H2S, mercury salt, etc. Okay, so enzymes are made poisonous by heavy metals like silver, mercury, and etc. And also enzymes are also destroyed by the certain substances like HCl, H2S, mercury salt, etc. This is the seventh one. Means what? They can be made poisonous by using the metals. Okay, and after that what? They can be also destroyed by using the certain substances. Now 8 characteristics feature and last one characteristic features of the enzyme catalyst. In certain enzymes, the non-protein part which is there, okay, in certain enzymes, non-protein part in certain enzymes non-protein part called coenzymes is present, and it increases the efficiency of enzyme. What it will do, it increases the efficiency of enzyme. Means efficiency means working power, they will just increases enzyme. It act as an what? It act as an promoter. Okay, it act as an promoter. Metal ion like Na plus, Cu plus, Mn plus, Zn plus, Co plus, etc. act as an coenzymes or promoter. In such enzymes, the protein part is called as what? Apoenzyme. Okay, so what I want to tell you is that consider this is our enzyme. Okay, inside of that enzyme, protein part is there, non-protein part is there. This is our protein part, this is our non-protein part. Consider, okay, this protein part which is there, I will write here protein part. We used to call it as an apoenzyme. And non-protein part which is there, we used to call it as an coenzyme. Let's take once again glance on all 8 characters. First character, enzymes are highly specific in the nature. Their action is different at a different catalyst or different reaction. So this is similar to the key lock arrangement, how the lock and key arranged for one another. Same way, different enzymes for different reaction. Second, enzymes are colloidal in the nature and very efficient catalyst, and they function only in the solution media. One molecule of the enzyme can catalyze the transformation of 1 million molecules of the reactant per minute, and they function with very low activation and they never need high amount of activation energy. They functions very low activation energy. Third point, they increase the rate of reaction or about 10 to the power 6 to 10 to the power 7 times. Fourth one, they are very sensitive to the temperature. So optimum temperature range is for about 37 degrees Celsius, or you can tell in the Kelvin 310 Kelvin, that is body temperature. They are permanently get deactivated or destroyed when you heat it or about 60 degrees Celsius. After 60 degrees Celsius, they just get destroyed over there, or 340 Kelvin. When you heat it, they just get destroyed. Sixth one, enzymes activity just depend upon the pH range, and the pH, most of the enzymes are found to have an optimum pH value is about 7.4, that is the pH of blood and other body fluids itself, that is 7.4 pH. They are having the activity in between this only, 7.4 pH. Seventh one, enzymes get poisoned by or get poisonous by heavy metal just like of silver, mercury, etc. And also enzymes can be destroyed by the certain substances like HCN, H2S, mercury, etc. itself, isn't it? And in the eighth one, in certain enzymes, the non-protein part of the enzymes covered which will be there, that is called as coenzyme, which is present, increases the efficiency of enzyme. It is also called as what? Promoter. The non-protein part is also called as what? Promoter itself. And the metals like Na plus, CO2 plus, Mn2 plus, Zn2 plus, CO2 plus, etc., which can be act as an what? Coenzymes. And the protein part of the enzyme is called as what? Apoenzymes itself. Here non-protein part can be act as an what? promoter itself. And now next part or next class we will going to deal about the Michael-Menten equation, that is mechanism or kinetics of enzyme catalyzed reactions itself, which is very important part as an exam point of view. There you will see how the substrate and enzyme they will form complex and product.